We're coming to the second Scott lecture. Where again, as we did the introductions in the first lecture, this is a 3-lecture series. It's quite an extraordinary arrangement. It's been going on since 1930, with Niels Bohr being the first one. It's wonderful, even at this in 2026, to be able to continue doing this. We have an expert, world-recognized expert, with us for a whole week. So if you haven't met Stuart Parkin, it's on you. You should please do sign up if there are any free spots left. Stuart is around till Friday. And here we're in the second lecture, which I'm particularly very keen. The second lecture is on 2D van der Waals materials for spintronics. I won't take any more time. Stuart, the floor is yours.
Okay, well, thank you very much for that introduction. And I'm very pleased to give this second lecture. Today, I thought I would focus on the 2D van der Waals materials, and in particular, how they can give rise to very interesting spintronic properties. And here I'd like to acknowledge my students and postdocs who've contributed to this work. They're shown in green, and also a collaboration with Evgeny Zimbel at the University of Nebraska. So actually, transition metal dichalcogenides, which is one member of the family of these 2D van der Waals materials, it was the subject of my PhD thesis, which I completed here in 1980, a long time ago. And I'm very pleased that Richard Friend is here. And he was actually, I followed his initial work on this topic. I'm not going to say too much about this. It turns out these, if you take niobium disulfide and tantalum disulfide, these form highly covalently bonded sheets. And between the sheets, you have the so-called van der Waals gap, in which you can insert, in this case, the first row transition metals. And it turns out at two particular concentrations, they form ordered arrangements, a root 3 by root 3 and a 2 by 2 superstructure, in which magnetically at relatively low temperatures, either ferromagnetically or anti-ferromagnetically. And so we did a lot of work and demonstrated how this could happen. And later on, just more recently, these materials, all these years later, 40 years later, have become of renewed interest. And it's been discovered that some of these show very interesting chiral structures. I'm going to come back to this a little bit later in my talk. However, actually, in my own department in the Max Planck Institute in Halle, we have quite a lot of projects in this field. And there's not enough time to discuss all of these projects today. So I want to give you just a brief overview of some of our work in these 6 particular fields. And the first one is something I want to talk about on Friday. And this, in 2022, we discovered something called the Josephson diode effect. You take a Josephson junction, 2 superconducting electrodes coupled through a 2D van der Waals material, turns out it's nickel ditelluride, and you see that the critical supercurrent going to the left and to the right have distinct values. In fact, they differ by up to 80% in the presence of small magnetic fields. I'd like to discuss this on Friday. It's a very, very interesting phenomenon. It relates in particular to the formation of triplet supercurrents. On the other hand, something I'm not going to talk about are the 2D ferroelectrics. And it turns out there's a whole family of these monochalcogenides, for example, tin selenide and tin telluride. And these, in a single monolayer form are ferroelectrics with in-plane polarization. The next layer is actually very interesting. It's an anti-ferroelectric. So the next monolayer will be coupled antiparallel to the first one. What we've shown is we can actually build interesting valve structures with monolayer electrodes formed from one of these ferroelectric materials. And in between, we have a paraelectric lead telluride. And depending upon the polarization directions of these layers, you can see that the tunneling properties are quite different. This paper was just published in Nature Communications, in case you're interested. So today I want to talk to you about how we can build a very interesting novel tunnel junction from all anti-ferromagnetic 2D materials. And at the same time, I also want to mention that we can flow current into some of these magnetic materials and see the motion of domain walls. And it turns out these domain walls have very high mobilities compared to conventional materials, perhaps reflective of the perfection of the structures of these layers. And so twisting of 2D materials is again another huge area within this field, which is hugely interesting. And we've used twisted monolayers to create novel tunnel junctions I'm going to discuss today, as well as interesting barriers for Josephson junctions, where we can prove that these non-reciprocal superconducting effects are truly related to the crystal structure. They're intrinsic and not extrinsic. And then something I'd also like to briefly discuss today is that these structures, it turns out, although I said they're perfect, they actually have defects that lower their symmetry and allow them to exhibit, in particular, some forms of magnetic skyrmions that I discussed in my first lecture. And then finally, of course, these materials are very interesting because you can make monolayers and therefore explore, from a fundamental point of view, the magnetism of two-dimensional sheets. And this is very difficult to do with any other material, but because of their very weak interactions with, let's say, a substrate, we use graphene, then we can explore the fundamental properties of a single magnetic sheet and show what type of magnetic behavior it exhibits. And I'd like to discuss this. And then finally, I'd like to discuss just a paper recently accepted in Science, where we believe we found the very first two-dimensional spin glass. So I'd like to talk about that subject as well. So first, let's go back to a magnetic tunnel junction. So I mentioned in my lecture on Monday, the magnetic tunneling junctions are very important for sensing tiny magnetic fields, primarily used in magnetic disk drives. And on the other hand, if we design them differently, we can engineer them so they can have two non-volatile states in zero magnetic field, which therefore can be used as a very interesting non-volatile magnetic memory. And this memory has become a foundry technology just a few years ago in 2019, and is becoming ever more important for all sorts of applications. So shown in this figure is a characteristic of the type of magnetic tunnel junction used in these technologies. And it basically is comprised here of two layers formed from magnetic cobalt iron, separated by a thin barrier, an insulating barrier of magnesium oxide. And these systems, as I mentioned on Monday, show very large changes in their tunneling conductance or their tunneling resistance when you switch the magnetic direction of one of these layers from being parallel to being antiparallel to the other layer. And the change in conductance is related to the polarization, the spin polarization of the tunneling current. And in some structures, the tunneling current can be spin polarized up to more than 90%. This leads to very large changes in tunneling conductance because the magnetic layers will only allow one type of spin polarized electron to pass. And today at room temperature, you see changes in tunneling conductance of several 100%, which makes them, as I said, very exciting and useful for some applications. However, there's one drawback. Today, actually, it turns out you have to switch the direction of magnetization by passing bigger currents, and these bigger currents deliver angular momentum and can apply torques on these layers. And that current today is 2 times bigger than the current available from a minimum sized transistor. So this is very important. We need to be able to reduce that current to fully take advantage of these devices. Another problem is that these magnetic layers have magnetic poles on the edges, shown here. And these cause interaction between these layers through the long-range dipole fields, both within and between structures. And it turns out they're also relatively sensitive to external magnetic fields, limiting their applications. So it's of great interest to imagine new types of tunneling junctions which are formed not from ferromagnetic materials, but innately from anti-ferromagnetic materials which have zero net magnetization. And on Friday, I want to talk about some very interesting results where we use a Kagome-Chiral antiferromagnet. And we can demonstrate that from a Kagome-Chiral antiferromagnetic layer with zero magnetization, we can extract spin polarized current because of Berry phase fields within the topological electronic structure of these materials. But, and these Kagome systems then, in 2 papers published in Nature in 2023 by a group in China and Japan, they demonstrated the first tunneling junctions which used these chiral anti-ferromagnetic layers, basically a conventional structure where you replace the ferromagnetic layers by these chiral anti-ferromagnetic layers. And one group reported at room temperature a change in resistance of about 100%. The other group, more consistent with our own work, only 2%. So this, nevertheless, is a very interesting ongoing topic. However, there's an alternative we could use. We have shown we could use some of these 2D magnets to create a different type of tunnel junction. And this is based on the original work of Xiaodong Zhu at the University of Washington. And in 2017, he demonstrated that this material, chromium iodine 3, which is a 2-dimensional van der Waals material, So one monolayer is separated from the next monolayer by essentially very, very weak bonding, the so-called van der Waals gap. And this material is actually insulating. And what he showed was, on the one hand, let's say in the top left, you can see, I don't know if this works, if you can you see this? Anyway, you can't see. The top left, here is the magnetization loop of a single monolayer. This material is magnetized out of plane. And so you see this beautiful hysteresis loop where in zero field, the moment is either pointing up or it's pointing down, this green and orange curve. This is an optical measurement where you use a magneto-optic Kerr signal to detect the change in magnetization with out-of-plane magnetic field. On the other hand, what they showed was that if you take two layers, then the two layers are coupled antiferromagnetically. So in zero magnetic field, then you have zero magnetization. And only when you apply a large field can you rotate the moments to become parallel in one direction or the other direction. And finally, if you take three layers, then you form a ferrimagnet, where essentially the layers are all aligned anti-ferromagnetically, but there's a net moment because you've got an odd numbers of layers. So very beautiful. And what they showed was that if they measured the conductance through these insulating layers, as shown here from top to bottom using graphene electrodes, then they saw that in zero magnetic field, the tunneling conductance is quite small. And in large magnetic fields, when the moments are oriented parallel, then the tunneling conductance, the current, is increased significantly by several 100%. So this is very, very interesting. So that's very interesting scientifically, but technologically, if you want to use it as a memory, not so useful, because in zero magnetic field, you have two states with the same resistance, so not very useful. However, a very beautiful result. So what we proposed, or this is my postdoc, Yuliang Chen proposed, well, let's consider a structure in which we use a very special van der Waals material. I'm going to discuss it on the next floor. That's chromium sulfur bromine. And this material, again, is one layer is ferromagnetic in plane, and the next layer is coupled anti-ferromagnetically. These moments are in plane. And our concept was, well, okay, we could build a structure where each layer, if you like, is formed from a one bilayer. So it has no net magnetization. So that we're going to form a 2D magnetic barrier formed from two bilayers as shown here. Okay, so now we can rotate the one bilayer magnetization with respect to the other one. And you see at the interface, in one case, the two moments, the red and blue arrows are antiparallel. In the other case, if we switch the bilayer, they will be parallel, and we would see a change in conductance. But again, of course, the structure wants the layers to be antiparallel, so this would not be useful to build a non-volatile device. So we supposed, well, let's twist the bilayers at a certain angle. And when we do that, we imagined that the interaction between the layers will be eliminated because the bonding we've changed. And actually, this is what we find. So our concept is we will form a twisted bilayer structure. And so this is, if you look on the side, this is the one, the green and the blue and green is not twisted, and the purple and red is twisted at each other. And now if you look from the top, you can see that the red and blue arrows of these innermost layers are at a large angle or at a small angle, nearly antiparallel or nearly parallel. And we found that these states are stable. So then we could build a structure which have inherently two distinct states. And that's what I'd like to briefly discuss in some more detail. So the material we're using is chromium sulfur bromine, which is a very interesting orthorhombic van der Waals material. Here is the structure. If you look from the top, the chromium sulfur and bromine is shown as blue, yellow, and red. And this is the structure from the top. You can clearly see that there's a difference in the structure going in the A direction and the B direction. And it turns out one monolayer is orders magnetically roughly the same temperature as the bulk, which is, it really is these individual layers coupled weakly together. If you look on the side, then you can see the red atoms of the bromine atoms, and in between you've got these chromium sulfur layers, and between the bromine layers from one van der Waals layer to the next, this is the so-called van der Waals gap, which is weakly bonded, but has an anti-ferromagnetic coupling when not twisted. So this is what Yuliang did. He basically made this structure by exfoliation. You exfoliate, in this case, just a bilayer, two layers, flake shown in red. This is not twisted, just to see how the properties look. And then you have these graphite electrodes to the top and bottom of the flake. And there's also additionally these large orange dashed layers and white dashed layers are hexagonal boron nitride, which we're using, as many groups do, to protect the whole structure from oxidation or from water. So chromium sulfur bromine is a semiconductor. It has this layered A-type so-called antiferromagnetism. And I just want to point out that the easy axis is along this B axis shown here, and the hard axis is the A axis. Okay, so now what do we do? So with this structure shown here, then we simply measure the current passing through this structure from these graphite electrodes. And what you find, this is the bilayer. So in a zero magnetic field, then the current is small, the layers are antiparallel. But if you align the field along the easy direction, which is the black direction, the B direction, you'll see nothing changes until a field, the so-called spin-flop field, where the magnetization will switch abruptly to the two moments being parallel. This is the spin-flop field. On the other hand, if we apply the magnetic field in plane along the hard direction, the B direction, the A direction, then you can see the red curve, the moments simply rotate gradually from being antiparallel to being parallel. It takes a bigger field. That's the idea. And then on the right-hand side, you can see a map of the tunneling current as we sweep the field from minus 1.5 Tesla to plus 1.5 Tesla for all angles in the plane of this bilayer flick. And you can clearly see that in zero field, the current is very tiny, it's black. And then at high field, it's very conducting. But you can easily see that along the B axis, the easy axis, you see an abrupt change from black to yellow. And along the hard axis, you see a more continuous change from black to yellow. So this reflects these curves here. But now we're plotting these curves at all angles between the easy and hard in-plane axes. And then reversing the field direction of centrally, you see the same. So these fields are too large, but nevertheless, this is what we see. Now we go to the case where we take two bilayers formed by exfoliation, twisted at some angle. This is nothing to do, let's say, with magic angle graphene. This is a 35 degrees, some arbitrary angle. And now this is a cartoon, so you can see here's the bilayer that's not twisted. Here's this bilayer on top, which is twisted at this 35 degrees. And now the idea is that these states we found will remain stable in zero magnetic field, where the innermost two layers, the two moments of the bilayers, will be either quasi-antiparallel or quasi-parallel. That's the idea. And this is the structure here. You can see this. You can see the two bilayers in red and in yellow, and the rest is again graphene and hexagonal boron nitride. So now again, if we look at the map of the tunneling conductance as a function of sweeping the magnetic field and as a function of the in-plane angle, you can clearly see now we can differentiate the easy axes, the B axis for the B axis for the top layer and the bottom layer, and the hard axis for the top and bottom layer, separated by this 35-degree twist. So we can clearly see this 35-degree twist as shown by these stars. And now what you can see is that depending upon, as we sweep the field, you see we get these black color, no current, very little current, but in the opposite direction, you see a more blue color, so the current is higher. So we have in zero magnetic field the possibility now of two states. So this works, but that field was too big, so we're upsetting the magnetizations. So now if we limit the field, you see between plus and minus 0.3 Tesla, you can clearly see now the regions shown by these arrows where we see clear two states in zero magnetic field. Here, this is low current, here, high current. So now we can create fantastic structure in which we see clearly in zero field two distinct states which vary by a considerable different tunneling current. Typically, this is what you see if we increase the bias voltage, then the tunneling conductance will decrease as we increase the voltage. So of course we can make structures with any arbitrary twist angle, or Julian can, and what you then see is if you have a small twist angle, the difference between the nearly parallel and the nearly antiparallel will become is bigger. You see a bigger difference in conductance for the two states in zero magnetic field. but it's less stable against magnetic field. If we have a larger twist angle, then the tunneling conductance change is much smaller. And at 90-degree twist, again, we reach a case where the two states in zero magnetic field have the same tunneling conductance. So we can vary the twist angle in this way. And very interestingly, the temperature dependence of the effect is also very, very interesting. So we can compare what happens if we have a very large magnetic field. So in that case, all the four layers will have their moments parallel, and you get a larger tunneling magnetoresistance compared to the case in which they're all antiparallel. But you can see as we increase, this is so it's untwisted, the black curve. So this very large 1000% tunneling magnetoresistance decreases with increasing temperature. The ordering temperature of each of these layers is about 120 Kelvin. But you see the twisted structure has a much weaker temperature dependence. And this again is because we've basically broken these bonds between the red and blue layers. And this means that essentially it's a more insulating system. So the electrons don't just get depolarized as they're passing through this device. So it's very interesting. Above 20 Kelvin, the twisted bilayer structure with the non-volatile states has a higher tunneling magnetoresistance than the untwisted case. Okay, so now, what is the origin? So now we collaborated with Evgeny Zimble, who can carry out electronic structure calculations. So he basically calculated the band structure for the case on the lower case, where the natural configuration of chromium sulfur bromine, which is antiferromagnetic, and then he can artificially put the layers to be parallel to one another in an artificial ferromagnetic configuration. And then you can see in this case, the red and blue bands correspond to the spin up and spin down polarized bands. So they're significantly spin polarized. And so now what we do is, this is what we do. We have the propagating states in the graphite electrodes, and we have this insulating material. The band gap is about, as you can see, 1 volt. And so the concept is we calculate the propagation through this is only a bilayer for spin up and spin down for the case in which the moments are parallel and the case in which they're antiparallel. And this is work by, as I said, these two postdocs and Evgeny Zimble. And so what do we do? He can calculate the complex bands, and therefore he can calculate the decay of these wave states through the bilayer, where you get these evanescent states decaying through this structure. And then this in momentum space, we can calculate the decay through these layers for the spin up and spin down electrons integrated over the Brillouin zone in the XY plane, perpendicular to the tunneling direction. This is what we do. So basically, this is the transmission probability. It's related to these evanescent decay, the complex wave function of these from these bands. And so basically, we can calculate for this, again, this case where the moments are parallel or antiparallel, then this is what it will look like. This is for spin up and spin down. This would be the decay. This is what the barriers look like. And then we can basically calculate what is the tunneling magnetoresistance from the decay of integrated over the Brillouin zone. And you see, the group at the Nebraska calculates tunneling magnetoresistance of 1800%. And we actually match that. We get 1000%. So we think that's pretty good agreement. So this is very nice. We think this is a pretty good result. But even more interesting, we can now, that was for a bilayer with no twist. Now we now have a twisted bilayer, but we change the angle. And then you can see this is the theoretical calculation shown in black. And this is how it decays as a function of increasing twist angle. As I mentioned before, eventually it will be 0 at 90 degrees. And these are our experiments where Yuliang has made all these different structures with different twist angles, bilayer structures. And you can see this fantastic agreement between the theory and experiment. So we believe this is the model that we have a system in which by the perfection of these layers, they actually look like, there's only 2 bilayers. They look like extremely good tunneling barriers with no defects that would spin depolarize the electrons. This is quite extraordinary. In the tunneling field, there are very few layers which you can create good tunnel barriers when they're very thin. This is only 2 bilayers, 2 layers of this van der Waals material. So we think this is very nice. And Yuliang then has gone, if you're more interested, you could read this paper just published in Nature.com, where he's demonstrated we can make a series of structures with more twisting of these structures And we can then create a series of states in this way, non-volatile states. And also, I'm not going to discuss, we've also demonstrated now that we can switch these states not with magnetic field, but with current. And the current, again, through spin torques, can switch these magnetizations. This is very, very important if we want to use it as a memory device. We use small currents to detect the state and larger currents to set the structure into different states. So we think this is a whole new field of very interesting tunneling junctions. Now, the only kind of small limitation is because the ordering temperature of this material is only about 130 Kelvin. So if we wanted to use it at room temperature, we need to find new materials. Nevertheless, it shows two things. Very interesting possibility to create an all antiferromagnetic tunnel junction with no stray fields. And I think this is very important. And that these van der Waals materials form excellent tunnel barriers. Of course, there's been a number of other groups who've demonstrated that particular point as well. So on Monday, I want to just switch now to domain wall motion in these systems. And on Monday, I showed you, well, okay, if you have a domain wall in a magnetic material, this is in plane, and you pass a current, the current automatically becomes spin polarized by spin-dependent scattering, and it can deliver spin angular momentum to the moments in the domain wall. And if the current is big enough, you deliver enough angular momentum, the domain wall will move. And it turns out the domain walls, successive domain walls, all will move in the same direction. And this is the basis of something I called racetrack memory, which I talked about extensively on Monday, so I don't want to talk about it in much detail. But just to remind you that if we have a nanowire in which we potentially could create it vertically, and we have a lot of projects in which we're using atomic layer deposition to make these structures vertically, we think it's possible, then we could put 100 domain walls in this structure, and we could then create a memory that would have very high density compared to nearly all existing memories, and would have very high performance because through a combination of either spin transfer torques or this spin orbit torque, where you spin currents generated through spin Hall effects in neighboring non-magnetic layers to generate even larger spin currents and a different type of torque on these domain walls, we can move the domain walls at speeds of up to 1 kilometer per second. And I mentioned we could detect them using integrated tunneling junctions or simply from the anomalous Hall signal from the magnetic component itself. And so this is what I showed. We can move these domain walls very nicely and detect their position in racetracks using a series of these anomalous Hall sensors built into the side of the racetrack. And again, you can read it. We published this paper in Science about a year ago. This, I think, is a very nice result. But what I want to go back to this, what I mentioned was we have to engineer these magnetic multilayers. And the structure, in this case, if we want to build a racetrack with an integrated tunnel junction, then we need some seed layers. We need this spin orbit torque layer to move the domain walls. We use a cobalt-based magnetic multilayer. Each of the layers is just a few angstroms thick. We need a synthetic antiferromagnetic structure in which we couple one magnetic layer to the next one so that they will be coupled antiferromagnetically and eliminate stray fields, which is very critical to nearly all spintronic devices. And then there'll be a tunnel barrier, typically in magnesium oxide, and then a reference layer for the tunnel junction, which itself will be one of these so-called synthetic antiferromagnets. So you have 4 magnetic layers, a pretty complicated structure. However, it's possible we can do this, and we can see we monitor the domain wall velocity as a function of the density of current density of pulses. Typically, we just put in nanosecond long current pulses to move the domain wall as shown in this magneto-optic microscope. We can detect the motion. And we find there's a critical current density before the domain walls will move. And it turns out that for useful devices, e.g. to replace the densest charge-based memory today, VNAND, then we want a very small critical current density to move the domain walls. In this case, this is a technical point. We can see velocities of the domain wall here of up to 400 meters per second. But in order to get very high tunneling magnetoresistance of this integrated tunnel junction, then there's some compromise we have to play, which, again, I don't want to talk about, but it's sort of interesting. And here we spent, I have to say, quite a few years in engineering these structures to optimize the properties. And this was work funded by Samsung. So I'm very grateful that Samsung funded this work for the last 6 years. And actually, we have two different structures. On the one hand, on the right-hand side, this is a structure where the magnetic layer, one magnetic layer in the racetrack is formed from cobalt, and the other is formed from a cobalt iron boron. This is an amorphous material, but enables the growth of high-quality tunneling junctions on top. And in this case, all I want to say is that the velocities of the domain walls are pretty high, but you see the threshold current density could be reduced after 6 years' work to 30 megaamps per square centimeter. It's a huge amount of work. And as I mentioned on Monday, we optimized, for example, the spin orbit torque layer by making it a multi-layer. We optimized the RKKY coupling through these two magnetic layers by introducing two angstroms of tungsten. So it's a lot of engineering work and some physics. And on the other hand, down here, we have a different structure where the magnetic layers are now formed from a tri-layer, cobalt, nickel, cobalt, where each layer is a few angstroms thick. The whole tri-layer is 1 nanometer thick. And here we could reduce this critical current density to about 20 megaamps per square centimeter. You have to remember that number, right? That's the number. The best number anybody has been able to create, and it took several years of work. Now, we now look at this 2D Van der Waals material, iron 3, gallium, tellurium 2. The structure is shown here. You have tellurium, these layers on the outside, and in between you have 3 iron layers. The middle iron layer contains some gallium. That's what it is. And you see here's the clear Van der Waals gap between these successive layers. And what you find, this material is the only Van der Waals material which is ferromagnetic above room temperature. Its ordering temperature is about 340 Kelvin, as shown here, from the magnetization versus temperature. Now here is I think, can you see, this is a Kerr image of a domain wall moving by spin transfer torque, by the current passed through it in a flake of this material. The flake is about 20 nanometers thick. And you can see if you measure, this is the velocity of the domain wall as a function of the current density in these pulses used to move the domain wall. So it's 20 times 5 nanosecond current pulses. And you see the threshold current density is only 3 megaamps per square centimeter. So it's 10 times lower. Without any engineering, this took 1 week to make a racetrack from this flake. So this is amazing. And moreover, this is at 50 Kelvin. So I didn't tell you, these previous work, this is all room temperature. And if we cool down, then the threshold currents increase enormously. So it's very difficult to move the domain walls. So this is remarkable. We can move the domain wall at temperatures as low as to the lowest temperature we go to, and the threshold current density is very, very tiny. So this is amazing. It's 10 times lower than the best conventional racetrack. That's remarkable. No work needed. So that's pretty nice. And turns out, even though this velocity seems kind of small, 25 meters per second, turns out that is actually that's extremely fast. It's the fastest domain wall motion with current pulses in any Van der Waals material on one hand. But if you measure, we'll just in the next fall, I'll show you, it turns out it corresponds to all the spin angular momentum in those current pulses being 100% transferred to that domain wall. So I just wanted to mention here then, the domain wall mobility here then in this work is whatever the units are, 37, compared to these cobalt nickel multilayers of 5. So it's much, much, much bigger. That's how easy it is to move the domain wall for a certain current density. So it's incredibly easier to move using spin transfer torque than in conventional materials. And as I mentioned, we can move them to very low temperatures. And even at room temperature, then the threshold current density is even smaller. It's only 1 or 2 in these units of megaamps per square centimeter. So it's a very nice result. We suppose this is because of the flatness and the uniformity of these layers as compared to our multi-layers with angstrom thick layers, where there will be variations in thickness, local variations in anisotropy, and local variations in other properties changing the pinning the domain walls. So this is a very nice, interesting result. And we can use conventional means of measuring the spin polarization. Here we use point contact spectroscopy. Here's the iron gallium flake, gallium tellurium flake, and we use a 2H niobium diselenide, which is a 2D Van der Waals superconductor. And by measuring the conductance from the magnetic ferromagnet into the superconductor, we can determine the polarization of the current by magnetizing the niobium diselenide. And we find a spin polarization of the current of about 40%. It actually corresponds pretty well to, let's say, the spin polarization in cobalt or nickel. Now, also wanted to mention that I was talking about this iron 3 gallium tellurium 2. I actually want to switch now to close cousin, same structure where gallium is replaced by germanium. And it turns out now, at the same temperature, you see the mobility in this close cousin is 10 times smaller, and the threshold current density is 6 times higher. And this turns out to be that the main walls are narrower in the rightmost material compared to the leftmost material because of the higher perpendicular magnetic anisotropy in this material. So that you see, even in the van der Waals materials, small changes in structure can make dramatic differences in their spintronic properties. So now I just want to mention this. I mentioned skyrmions on Monday, and it turns out this material should not show skyrmions because it has a centrosymmetric structure which does not allow for these vector exchange interactions called this Dzerzhinsky-Maria interaction. But this is just to show you that indeed, using Lorentz transmission electron microscopy, where we pass an electron beam through a very thin layer of the sample, which we take out of a single crystal using focused ion beam milling. And here you can see a beautiful array of these skyrmionic objects. And we know that they're nail-like because we only see any contrast if we tilt the sample with respect to the incoming beam. Anyway, this is a technical detail, but we can clearly see these beautiful skyrmionic objects which should not exist because this nominally is a centrosymmetric material. So that's a surprise. So why is this? Okay, also these skyrmions, very beautiful. You can see that as you increase the thickness of we make a layer whose thickness varies from the left to the right or from the top to the bottom. And you can see from 100 nanometers thick to 2 microns thick, it's too thick to use Lorentz transmission electron microscopy. So we simply use here magnetic force microscopy, where we scan the magnetic tip of the surface. It measures the out-of-plane magnetization. It can't determine whether they're nail-like or block-like skyrmions. And just to remind you, a nail-like skyrmion is one in which it's a small object, you typically formed in arrays, and the magnetization rotates from an up direction on the outside to a down direction on the inside, and you see the magnetization rotates parallel to the radius of this object all the way around. This is called a nail skyrmion, and it's a topological object. So here, the size is changing because of dipole-dipole interactions. Anyway, I want to say this. So now, why do we see them? So it turns out now we have a very interesting, well, first, we have a fantastic guy, Holger Meyerheim, did these measurements. Secondly, we have a very interesting X-ray source. It's based on dripping gallium metal, and you use very high energy electron beams to create X-ray source. It's about 200 times as intense as a typical laboratory source. This enables us to detect the structure of these very thin layers. So what do we find? We find that this material, even though it has this perfect structure for domain wall motion, actually has two types of defects. On the one hand, if we look within the layer, you see this site 6 in one layer and site 5 in the next layer. Turns out they're not fully occupied by iron. They have some vacancies. And this one here, you see the best fit to our data is this one has 92% occupancy and this one 87. So they have slightly different occupancies, which lowers the symmetry, we believe. That is explaining the non-centrosymmetric behavior. Okay, on the other hand, what we see is within these van der Waals gap, we find evidence for iron. So it's about 15% occupancy of these sites by iron. So that is a very interesting structure. So this is what we said. So with these, we have, in some sense, disorder. The sites here in successive van der Waals layers are not equally occupied. And this is shown, you can't see it here, but on the right-hand side, this is the difference in the integrated charge density through the whole unit cell, compared to a model in which we have no iron in these sites. And you can clearly see that there's excess iron in these van der Waals sites. So what does it mean? It turns out it's actually, we think, very, very interesting. It turns out you have a set of iron atoms which are randomly distributed and randomly interacting. And so this leads me to briefly remind you that these 2D materials then are very interesting for looking at, from a fundamental point of view, what is the type of magnetism present? So as you all know, there's a famous theorem, the Mermin-Wagner theorem, that says in 2 dimensions, if there's no anisotropy, then there can be no phase transition. They cannot form an ordered magnetic state. This is also true for 1-dimensional systems. And now in 1973, there was a so-called BKT model, Thales and Kostelitz, Berezinski, which found very interesting. In 2 dimensions, you can actually have a phase transition in which below some temperature, you form an array of magnetic vortices and anti-vortices, sort of akin to the skyrmion we discussed earlier. And this could allow for phase transitions in a 2D layer in this XY model. Well, I mentioned 2017 was when the first monolayer van der Waals systems which become ferromagnetic were found. And then this is our own work. This is a paper we published in Science a few years ago in 2021. And we found we could grow by molecular beam epitaxy a single layer of chromium chlorine 3. So before I mentioned chromium iodine 3, which is magnetized perpendicular, this material is magnetized in plane, but there's no anisotropy. So the magnetization can rotate in any direction. And moreover, by growing this by molecular beam epitaxy on large areas, it enables us to carry out measurements not otherwise possible. And we grew it on graphene, and it turns out there's no interaction between graphene and this layer. So it really is the first 2-dimensional XY layer. And here is, you see, for example, here, this is an SDM image of one monolayer grown by molecular beam epitaxy on graphene. And this is an interference image. They're slightly rotated with respect to one another. So it's like a moire lattice here. And we found that this one monolayer, by using X-ray magnetic circular dichroism to measure the magnetization as a function of temperature, we could determine the critical exponent. How does the magnetization vary with temperature? And clearly, the best fit was this 2D XY model. So the magnetization can align in any direction. We think this is a reflection of this BKT transition that I mentioned earlier. So this is very interesting. In these 2D systems now, one can find antiferromagnets. I discussed chromium sulfur bromine. One can find ferromagnets, monolayers, which are magnetized in plane or out of plane. There are Ising-like systems, Heisenberg-like, our own XY-like systems. All of these have been discovered. However, these are ordered phases. And in this period of time, there was tremendous interest in spin glasses. And so I want to discuss this, that we think, well, first the question is, can you realize a spin glass in a 2D van der Waals materials in the monolayer limit? And well, does it survive to the 2D limit? And we want to address this. So just to remind you, what is a spin glass? And so you have a solid, you have a gas, you have a liquid, and of course, this is what we have. And okay, so ferromagnetic ordering of this type is like a solid. You can have a paramagnet. You can have spin liquids, which I'm not going to discuss, which are very interesting. And you can have a spin glass where the moments are randomly ordered in this way. And so what does it mean? That means that locally, if you measure the magnetization on a single site, then on these solid, in the ferromagnet, antiferromagnet, the moment will point in one direction or the other. And in all these cases will be 0. But in the case of a spin glass, it will also be in one direction or the other direction. This is this distinction from a spin liquid. And but on the other hand, if you add up all the moments and all the sites, only for a ferromagnet will you find a net positive moment, or on the sublattice of the antiferromagnet. In this spin glass, it will be 0. So that's what we want to do. And so, okay, so then we've talked about this. So I want to point out then that very interestingly, so a solid like a ferromagnet, there will be one ground state. No matter what you do, it will essentially go to that ground state, magnetized in one direction or the other. However, a spin glass is very interesting. There are many different states. So if we freeze the system, then it'll go to this minimum energy site, metastable state. You freeze it another time, it'll go to a different one. There are multiple different configurations of these spins. Each one is different. Many degenerate ground states. A lot of frustration in this way. Okay, so how to stabilize this? Well, quench disorder, frustration. This is what we do. And typically, one takes a system, dilute system with spins like manganese atoms, manganese spins in copper. And in copper, as I mentioned in my talk on Monday, you form a spin density wave where the copper becomes spin polarized, and because if you only have available electrons with momenta up to the Fermi momentum, then they can incompletely screen the moment, in this case, let's say manganese, and so the copper will be spin polarized and with a spin density wave, which will allow for a second spin to interact either ferromagnetically or anti-ferromagnetically, depending upon the distance. This is the idea. And so we have this concept, if we change the concentration of these moments, with high concentration, you have a ferromagnet, limited concentration can be paramagnetic, but for intermediate, you could imagine a spin glass. That's the idea. Okay, competition between these different interactions. And so now, going back to our iron 3 germanium tellurium 2, I mentioned on the one hand, we have a ferromagnetic lattice within the van der Waals structure itself. And as I mentioned earlier, this is magnetized outer plane. But within the van der Waals gap, you have these 15% occupancy of sites that we discovered, you have random spins. And so we think these actually form a spin glass. And so how do we, okay, this we talked about earlier. So we think these excess iron will form a spin glass. And how do we look at that? And of course, one signature is when you cool down the system in different magnetic fields, you get different responses, but that would happen to many different systems. But the one key measurement is to carry out AC susceptibility at very low frequencies. And as you increase the frequency, the spins become essentially cannot respond. And so this frequency-dependent AC susceptibility is often regarded as a key signature of a spin glass. But this is a famous paper by Binder and Young on the manganese dope with copper, and you can see that the susceptibility then has a strong, this is as you vary the frequency, and now this is our own measurements for this iron 3 germanium tellurium 2, and what do we find? We find this is the real part of the susceptibility, this is the imaginary part, and by the way, this is on a single crystal, it's not a single monolayer, and we see clear, particularly in the imaginary part, you see this peak in the susceptibility decreases substantially as we increase the frequency of the AC field excitation. The AC field here is a few Ørsted from 0.1 to 55 Hertz. This is a signature of a spin glass, we believe. But interestingly, as I said, it is taking place in a system in which we also have, at a higher temperature, a magnetic ordering. So this is a very unusual case where you can see a spin glass characteristics in the presence of a host magnetic material. So this is just a cartoon. As I mentioned earlier, we expect in a spin glass multiple states differing in energy a little bit, which are metastable in this way. Okay, so whereas a ferromagnetic system, you have two ground states, moment pointing in one direction or the other. So this is what we see. In addition then to this frequency-dependent susceptibility, then we also see that if you measure that susceptibility over time, then it decreases. And this is because the system is metastable and is moving to other states. And this is what you see. This is taken at a temperature of 176 Kelvin, which is just below the ordering temperature of the bulk magnetic behavior of the system. And we also see evidence for memory effects. So here we take a system, we look at the decay of the susceptibility, and you see if we change the temperature delta T by 0.2 Kelvin, nothing much changes. If we change it by a bigger amount, 2 Kelvin, then the susceptibility increases. You see this peak and then decays to a different value. However, if we change the temperature back to the original temperature, eventually it will decay back to the same metastable state as the first temperature. All of these are characteristic features of a spin glass. It shows, on the one hand, aging, the decay, on the one hand, chaos, this increase, this peak in susceptibility, and on the other hand, a memory effect, change the temperature, you go back to the original state. So all of these are characteristics. So that was a bulk single crystal of this material. Now, what about a single flake? So it's very difficult to do this using EG, a state-of-the-art squid magnetometer. Turns out it cannot do it. So what do we do instead? We built, a little coil shown here. You see the coil to create a small magnetic field, and we actually measure the whole signal on a flake. We make contacts, measure the whole signal, and then in this way we can measure the response down to thicknesses of 17 nanometers or so. still not one monolayer. So we can also use Kerr microscopy to measure the magnetic moment, and again measure the AC stability. Is pretty good. And so how do we measure response from one flakes? Well, actually, we just, okay, this is to remind you, okay, now we've exfoliated from a single crystal, a wafer, which is varying in thickness from one layer. And okay, the idea here was to remind you, one layer is actually this two van der Waals layers. This is one, we're going to call it one monolayer, one unit cell. Okay, anyway. And then we can find, by measuring the Kerr locally on this portion, this one monolayer, we can detect the same frequency-dependent AC susceptibility response. So we think this is very good evidence that this flake, just one monolayer thick, exhibits a spin glass, the first two-dimensional spin glass. And here's, you see from the temperature thickness of the flake phase diagram, you see what we see is the green curve. The green dots correspond to the ordering of the ferromagnetic layers themselves. And a few degrees below that, we see this evidence for this spin glass freezing of the moments within the van der Waals layer. And of course, you could also see here that the ordering temperature, the magnetic ordering temperature of the bulk, decreases significantly as we go from bulk down to a single monolayer, shown here. So interesting, what's the dimensionality, what mediates the coupling? Most likely some kind of RKKY through these tellurium layers, and so on. What about it? Anyway, so we think this is very interesting. There are also other disordered phases that could be available. Finally, I just want to mention, we can actually grow these van der Waals materials, let's say iron 3, germanium, tellurium 2, by molecular beam epitaxy. So this is very important if we want to make larger areas beyond a few square microns of exfoliated flakes to carry out certain types of measurements, especially for ultra-thin layers. And this is grown in my department by Rufeng Wang, excellent postdoc. And actually what I want to show to you is, turns out disorder still very important in the structure. And so whilst these higher order layers look perfect, they look very much like the structure I showed you before, it turns out that if we look at the scaling behavior, in other words, how does the magnetization vary as a function of temperature for one monolayer, which is shown here in this curve here, one monolayer, or two monolayers, or 3, 4, 5, 6, then what we find is that one monolayer actually looks like a 3D magnetic system, a Heisenberg system, from its critical exponent. And 2, 3, and above look like a 2D icing system, which is what you would expect for this system with perpendicular anisotropy. And the reason is that a single monolayer grown by molecular beam epitaxy in this way has a structure which is strongly distorted. It breaks Lowes symmetry significantly, as shown here. You see these are germanium layers, which should be here, but you see they're here. So this is quite amazing. So the germanium is moved to the top in the first monolayer. And this is by the way, by the structure here is determined by X-ray diffraction I mentioned earlier. And this MB structure also shows the same self-intercalation of ions in the van der Waals gap, roughly with the same, same 15% occupancy. So this is very interesting that we have a system we can grow by molecular beam epitaxy. It also shows skyrmions, and it shows the same structural defects, these ion vacancies that vary from one layer to the next, and so on. Okay, now I'm going to skip this. And I also wanted to just briefly mention, I should probably finish, but we've also found recently a second system in which we see long-range magnetism plus a spin glass. And again, this is really interesting. I mentioned in my first foil, my PhD was about tantalum disulfide intercalated with iron and all the first row transition metals. Here we've grown this system, iron 0.28 tantalum disulfide. So it's in between a quarter where you see a 2x2 superstructure and 1/3. And it turns out this system shows a √3 by √3 superstructure. But if we look at the structure again in detail, we find that there are 2 van der Waals layers and 2 van der Waals gaps. And so you have tantalum disulfide, and the first van der Waals gap, nearly 30%, 33% of iron. So you have a √3 by √3 superstructure completely filled with iron that orders magnetically. The next van der Waals gap, you have much less iron, 10%. And this, we believe, gives rise to this spin glass behavior. So naturally, the system forms a complex structure with successive van der Waals gap containing a lot of iron, little iron, and vice versa. So it's really quite amazing. And well, we can tell all this from, this is just to show you the superstructure. And then this is to show you, we can see skyrmions in the system. So it has this lowered symmetry because of this complex occupancy of iron in these different sites. And it also shows spin glass-like behavior if we look at the real and imaginary parts of the AC susceptibility as a function of frequency. You see this shift in the peak. So this is another system in which we can see spin glass characteristics because of an incomplete occupancy of one of these van der Waals layers. It also shows aging and chaos. So let me summarize by saying, well, 2D van der Waals materials are really exciting and interesting. And in the first part of my talk, I wanted to show you that they form almost perfect tunnel barriers. And by forming a tunnel barrier from a very interesting orthorhombic system with a bilayer where the two layers, actually two bilayers, where the innermost layers can be nearly parallel or nearly antiparallel, we can see huge tunneling conductance changes, and yet the net bilayers have no net magnetization. I think this is very interesting. And by twisting these layers, we can show with excellent agreement with a model in which we look at how the spin-dependent, the spin-polarized electrons decay through these structures. And finally, we've shown you that the domain walls can move with very high mobility in these structures, reflective of the perfection of the layers, yet these structures actually have significant defects. They lower the symmetry from centrosymmetric structure to a non-centrosymmetric structure, allowing for these vector exchange interactions and the display of skyrmions, which is very interesting. And at the same time, we find evidence in both single crystals grown by conventional means and MBE films grown by MBE techniques that we also see iron in the van der Waals gaps. And these appear to be spin glass-like in characteristic, and we believe we can take a single model there and show these first 2D spin glass behavior. So, summary, van der Waals layers on the one hand form excellent tunnel barriers, and on the other hand, they contain defects that change fundamentally their properties. So thank you very much.
Thank you very much, Stuart. Fantastic talk again. Questions?
Hello, thank you for the interesting talk. I was wondering if you could elaborate a bit more on the new device opportunities that emerge from these mixed spin glasses, magnetic phases.
You mean the opportunities you said?
In terms of devices or, you know, how can we take advantage of this in the best way?
Well, actually, I think this is, I think what it reflects rather is the structures are not as perfect as you might otherwise expect. And so these properties, the ones I discussed, are reflective of those changes in structure. And it turns out that if you can, you can introduce the defects that can change the symmetry and allow for spintronic properties that are not otherwise available, I think that is the opportunity. And at the same time, actually, I think a huge opportunity are these tunnel barriers. The tunnel barriers, conventionally, they're like three materials that form high-quality, ultra-thin tunnel barriers. I think this opens the door to a whole series of, tunnel barriers that could be useful in, let's say, conventionally, you want to be able to tune the tunnel barrier height for different applications. So I think this is very, very interesting. I think the fact that these form these perfect tunnel barriers, even though they have these very interesting defects. So I think, and also I think what's interesting, what I want to talk about these defects is that if you don't carry out very careful structural data, it's very easy to say, oh, the structure is just what everybody has reported before, a centrosymmetric structure. Actually, you need to carry out very, very sensitive X-ray structure on these ultra-thin layers, which is non-trivial, to show that the imperfections, let's say, the fact that this material, iron 3, germanium, fluorine 2, shows skyrmions. Other groups said, oh, the surface must be oxidized. This is how you break the symmetry. Well, made no sense and cannot be correct. So it's very difficult actually to prove that you have these very interesting perturbations in the structure from what nearly all groups have demonstrated. And in fact, we found now in like 5 different materials, not only van der Waals materials, like platinum, manganese, gallium, the structure is distinct from what people believed in that particular case for 30 years. And you have a lowered symmetry that in that case also we could detect through the observation of skyrmions, which should not otherwise be present. So I think this is a very interesting result, that these defects, which are actually intrinsic, as I said, like MBE and single crystals show the same defects, the same variation from one van der Waals layer to the next, these ion vacancies, plus the self-intercalation.
Thank you.
Henning?
Oh, very careful.
Thank you, Stuart, for a great talk. How shall I think about how this spin glass survives the exchange coupling with the magnetic order? I mean, do these spins sit on its side where the exchange fields from neighboring layers cancel each other, or how is it possible to retain the spin glass?
So I think this is, we don't really know the answer to that question. A very interesting question. And it could be that, the ion then is basically coupled to the tellurium, and the tellurium could be overlapping very large atoms. It could be through these tellurium array of the tellurium atoms itself. Typically, let's say in manganese in copper or other systems, even the tantalum disulfide with the first row transition metals intercalated, we showed by polarized neutron scattering that the innermost van der Waals layer is itself spin polarized. It forms basically this spin density wave. So in that case, it's through this structure is a little bit different. And so we think it somehow the tellurium layers themselves play a key role. Yeah, I agree. Yeah, I totally agree. So we don't know the answer to that, but we see this behavior, which is we know with all the measurements, aging, chaos, memory, certainly looks like a spin glass. But I think this is a key question.
Jeremy?
So I'm interested in the iron gallium tellurium system where you have these domain wall motion, which is very easy. But I'm interested, does domain wall pinning occur in the same way in these 2D materials with very smooth interfaces, or is domain wall pinning a very different sort of phenomenon?
Well, as I said, I think it's very different because in our multi-layers, you have a few angstroms of cobalt and nickel cobalt, and slight variations are inevitable. And that will locally change the anisotropy, for example, and that will lead to pinning sites. Here, it seems they're certainly more perfect. It doesn't mean they're totally perfect because we see these ion vacancies. So if these ion vacancies are not uniform, that could give rise to some pinning of the domain wall.
But then
variation
something like stochastic jumps over large distances. Do you see effects like that?
The domain wall jumping.
Yeah, between defect sites, if you're,
No, I don't think so. I mean, that's certainly an interesting question whether the domain wall could, for example, bend locally because curve because of local defects. This is not what we see, at least from optical measurements, where we can directly determine the domain wall. As it moves, the domain wall will actually tilt. We can see all these tilting mechanisms, but because of pinning, the domain wall remains tilted after you've removed the current. So pinning is very important. But it doesn't appear to, the domain was not going to jump from one state to the next. It's a more uniform pinning potential.
So they pinned at sort of single defect sites then? Is that what you're saying?
No, I don't think a single defect won't pin the domain wall. The domain wall itself in these structures is of the order of a few nanometers wide, in the range of 6 to 10 nanometers wide. So you need a lot of defects to pin it, not just a single one.
Judith?
Twisted layers. If you make a device with the twisted layers, I can see how you can do it with individual flakes and do the twisting, but how do you do that if you're going to make
that would be easy. We would just use, we could grow, let's say on 2 wafers, we could grow 2 monolayers, and then we can mechanically rotate, and this is a technique that's certainly possible. This is like a wafer scale bonding. It's possible to bond 2 surfaces together. So we could certainly, we're thinking of building a system like this, where we would have, create, let's say, since we know we can create these by FGT, for example, by ND. We could grow it on two wafers and then just using an internal robot, twist and put them together. So should be
Okay,
possible.
great.
And then we could also, we have many experiments where we use a sacrificial oxide layer to remove, so we could easily remove the second substrate by using this sacrificial oxide layer, which we've already demonstrated we can grow many of these 2D systems.
Okay, thank you.
So in the first part where you were talking about the twisted bilayers, your theoretical predictions assumed the conservation of the in-plane momentum, right?
Yeah.
And have you considered the crystal alignment of the tunneling layer and the two graphene layers as well?
Yeah, you mean the graphene layers?
Yes.
That we use? But I don't think that doesn't appear to be important. We made all of these devices where we don't worry about the relative orientation of the graphite layer or the graphene layer and the chromium sulfur bromine layers. So it doesn't seem to play a role because we see this beautiful correspondence between the experimental dependence of the tunneling mediated resistance on twist angle and theory. So we don't think that's important. But it's a very interesting question. Of course, it might be important if we use other electrodes formed from other metallic 2D systems.
And when you use FGT for tunneling, for the magnetic tunnel junctions, do you think the spin glass, the 2D spin glass, would affect the tunneling magnetic resistance?
Well, actually, if you really wanted to tunnel from the FGT as a magnetic electrode, and you had these random spins, if they were fluctuating, then they would probably depolarize the tunneling current. So it would be very bad.
But there is quite high efficiency as well from FGET and FGAT junctions.
Yeah, then then in those cases, we were moving domain walls. We were not making tunneling junctions. However, we have made tunneling junctions with FGT and tungsten diselenide as the tunnel barrier. And actually, we can see very high tunneling lead resistance from these layers. So you might expect these intercalated spins to influence, of course, depolarization, but we haven't seen that actually.
Okay.
We'll take one last one.
Yeah, so continuing on the main wall, sorry, for the meal. Okay, good.
Yeah.
Oh, yeah, thank you. So continuing on the domain wall motion stuff, in your cartoon, you showed like a head-to-head kind of card domain wall. Have you ever do you see motion in neutral domain walls? Have you looked at that, or is that something that's completely unreasonable?
No, you mean, so is there a difference between a head-to-head and tail-to-tail domain wall?
Or even head-to-tail?
Head to tail, for sure that means, but it's not possible. But anyway, head-to-head and tail-to-tail, they actually move at the same velocity in these experiments. Other experiments in which we can we can distinguish the motions in other types of systems with lower symmetry. I didn't really have time to discuss on Monday. We're actually very, very interested in imposing chirality in magnetic systems by, we're doing this in several ways. One is we build three-dimensional structures which essentially have curved and torsions, and we can impose geometrical chirality on magnetic systems. Alternatively, we're looking at a silicon wafer where you cut it at a very high index, SFE643, and that surface has a chiral surface with steps. And in that case, we would see differences in the current-induced domain wall motion for up, down, and up, down, and head, up, down, up domain walls.
Okay, thank you.
All right, with that, let's thank Stuart again.
Okay, thank you. Good luck.
And we invite everybody to the reception upstairs.